we're going to talk about filtering, the filtering part of AC to DC conversion. Not the same as filtering like active filters or passive filters, but a different kind of filtering. So recall that when converting AC voltage to DC voltage, we have 4 stages. We looked at diode rectifiers last week, and this week we're going to look at the filtering part. The voltage regulation and load part is not covered in here. We do cover the rectification and the filtering part. So the basic understanding is that pretty much all half-wave and full-wave rectifiers use some kind of capacitor to filter the signal. It takes harmonics out and it passes the DC part of the signal, and the DC is actually better and higher than without the filter. It also reduces the variation in the output voltage to an extent. So the basis of all filter capacitors is something known as a peak detector. So we're going to look at those first, and then we're going to modify them a little bit to look at how you would make a half-wave rectifier or a full-wave rectifier with a capacitor. So a peak detector uses a diode and a capacitor, and it basically captures the peak of the waveform and holds it until the next peak occurs. The diode passes the positive part of the input, and the capacitor charges, and then when the waveform starts going down again, decreasing, the diode is reverse biased, and the capacitor just holds on to that value. So if we assume the diode's ideal, then basically the signal would rise and just hold at that peak value. And that peak value, V out, would just be a stable peak value and it would not change. However, you generally don't use a peak detector by itself with no resistance. So basically we're going to look at what a half-wave peak rectifier would look like. And in order to do that, we have to add a resistor to the circuit. And when we add a resistor, then there is an RC time constant that causes an interaction between the capacitor and the resistor, and the capacitor discharges between the positive peaks of the waveform. Every time the capacitor voltage matches the input voltage, the diode will conduct in order to allow the capacitor to recharge in every positive cycle. So what this looks like is basically a ripple. We end up with a peak value that decays between points, and then it recharges every time the positive waveform reaches a point where the voltage is going to be larger than what the capacitor has charged to. And what you get out is a peak-to-peak ripple voltage. When the diode's not conducting, then the capacitor will discharge through the resistor, and the time that it discharges is between the peak of the preceding waveform and the point at which the next waveform reaches a voltage that exceeds the voltage in the capacitor. So that's a pretty long time that it discharges. And then the diode conducts during that brief time when the capacitor voltage is equal to the input voltage, and then it stops when the input reaches its peak value again. So there's a very short period of time when the diode conducts. In order to minimize the rippling of the voltage, because what we really want is a stable DC voltage at the very end of this whole process, so we want as small a ripple as possible, the RC time constant needs to be much greater than the period of the waveform, which is not difficult to do. It's pretty easy to do that. And even if we do this, there still will be a certain amount of ripple voltage that is present. So, first of all, we want to know how to find the DC value of the output. And we're going to make some assumptions to go into that. First of all, we assume the diode is ideal. We know it's not, but we're going to assume it is. We assume the RC value is much greater than the period of the waveform. And we're going to assume that the discharge time is approximately equal to the period of the input waveform. We know it's not, but the charging time is going to be really small and the discharge time is going to be large. So we're actually going to approximate that by saying it's equal to the period of the waveform. We're also going to assume that the ripple voltage is basically a triangle. So when we look at a picture of that, you can see it kind of sort of looks like a triangle, and the DC voltage is going to be the average of that. And if you look, you can see the part of the waveform that exceeds the DC value and the part of the waveform that is lower than the DC value is approximately equal in area. So that way, we basically take the ripple voltage, and in order to find the DC, we just take the peak value and subtract half the ripple voltage. So that's not hard, that's easy. The problem is, how do we figure out what the ripple voltage is? And this is a little more complicated. So to find the ripple voltage, first of all, when the diode turns off, the output is just going to be V peak e to the minus t over tau or RC. This is basically the same function that we looked at when you were doing charging and discharging and transients in capacitors when you were in circuits 1. So this is kind of a same discharging kind of waveform. So the next value that we're going to look at is the end of the discharge cycle. And at the end of the discharge cycle, we assume that the value of the diode discharge period is approximately equal to the period of the waveform. And when we do that, we can set V peak minus VR to be approximately equal to that. So this is making a little bit of an approximation, but it's not a terrible approximation. So since RC is really large compared to the period of the waveform, we can actually approximate that exponential, e to the minus t over RC. And we use the first two terms of the Taylor series. We get 1 minus the period over RC. And we just use that as kind of an approximation of that exponential function, which makes the whole process a lot easier. Therefore, V peak minus VR is approximately equal to V peak times 1 minus t over RC, which is equal to V peak minus V peak times t over RC, which means that we can use that to solve for VR if we just equate VR to V peak times t over RC. And we actually, since we usually know the frequency more than we know the period, we change it to V peak over F RC, which is a quite important equation when we are dealing with rectifier circuits. Also, make note of the fact that the load current is going to be equal to V peak over R, so VR can also be approximately found by taking the load current and dividing by the frequency times the capacitance. So that's kind of another way to find it. So now that we've got that, we need to look at the current through the diode, because the current through the diode is going to change depending on what's going on in the circuit. During conduction, the diode current spikes and gets really large and then decreases as the voltage difference becomes less. So we can look at the fact that during this small delta t time, basically the current in the diode peaks and then it drops off until it stops charging. So what we want to know about this, we want to know the maximum and the average diode currents just to make sure that the diode can handle the current when it's conducting. So how do we figure that out? Well, we start with taking the value of conduction time, which we need to know, and remember that's really, really small. But we need to find that conduction time in order to figure out what the current's going to be. So we know that V peak cosine 2 pi f delta t is going to equal V peak minus VR. So that's kind of just where the two waveforms reach. Now we know that 2 pi f delta t is a really small value. So we can use an approximation for that value. We can take 1 minus 1/2 2 pi f delta t squared, and that will approximately give us the value of that cosine function. Therefore, v peak times that value 1 minus 1/2 2 pi f delta t squared is equal to v peak minus vr. And you can kind of see that we're going somewhere with all this. We can divide everything by v peak to kind of get rid of that. And then we can take away the 1, the minus, and multiply by 2, and then take the square root on both sides, and we get 2 pi f delta t is approximately equal to 2 vr over v peak. So this value is the conduction angle. This is the conduction angle in radians. This tells us what that value is. We don't quite know delta t, but we can certainly figure it out easily if we know the frequency. So the conduction angle is where we take 2 pi f and multiply it by that change in time, and then the actual time difference would just be the time value itself. So we can find the conduction time by just taking 1 over 2 pi f times the square root of 2 vr v peak. So now that we have the conduction angle, we can figure out the conduction time, and then we can figure out the average current from that. The average current is just IL plus IC, which is equal to IL plus C dV dt, which is IL plus C times the ripple voltage, and the ripple voltage is just the change in voltage. That's how much it's going to change. And then the value of dt is just that delta t value. That's 1 over our delta t value that we already found. So once we have that, then we can change the equation a little bit. We can substitute IL equals FCVR. We just covered that a little bit back, but we found the voltage, ripple voltage was IL over FC, so we just moved that around a little bit. And we move the 2 inside the radical, so we can get that out of the way. And then we have the equation for the average current, which is IL times 1 plus pi square root of 2 V peak over VR. And the maximum current is almost the same. It's just IL times 1 plus 2 pi over 2 V peak over VR, taking the square root of that. So let's look at an example to kind of run those numbers through. If we have a 60 hertz sine wave and the input is V peak equals 100 volts and the load resistance is R equals 10 kiloohms, we want to find the value of capacitance we need to set the ripple voltage to 2 volts, and then we want to find the conduction angle and the average and peak diode currents. So first of all, the capacitance is just equal to V peak over VR FR, and we can calculate that out. We get 83.3 microfarads. And then the conduction angle, again, we just solve for it. That's 2 pi f delta t, so we take the square root of 2 VR over V peak, and we get 0.2 radians. The average and peak diode currents, again, just kind of plug in the values and get the answers. So we get IL, which is V peak over R, so we can get that value really easily. And then we take 1 plus pi and just substitute in 2 V peak over VR, and we get 324 milliamps. And then the maximum is going to be found similarly, and we get not quite double the current, but it's really, really close. It's almost double the current when it's at its peak value. So the only difference between a half-wave rectifier and a full-wave rectifier is the fact that the charging and discharging times are shorter. That's really the only difference. Everything else is exactly the same. In the ripple voltage, it's just half of that of a half-wave rectifier because the capacitor discharges over half the period rather than the full period. So we just use VR as approximately equal to V peak over 2 FRC. And then the values of the average and maximum currents, again, are also slightly different, but not majorly different. Instead of 2 V peak over VR, we have V peak over 2 VR, and we get almost the same value. So these are the things you need to know about filtering, and we'll cover the last topic on Wednesday.